Start now, sir.
Yes, sir.
Shall we start? Prashant sir? Prashant Jain sir? Okay. Oh, now here. Shall we start, sir? Prashant sir?
Hello.
Hello.
Hello. Good afternoon. Sir, am I audible?
Hello. Dr. Salin, yes, I am audible. I can hear you.
Yes, sir. You can present your screen, sir.
Hello. Am I audible now?
Okay. Yes, sir. Yes, sir.
Yes, sir.
Okay, sir. Okay, sir. Okay, sir.
Yeah, you give me recording permission to me. I think you are using this license version, right?
Yes, sir. सर को बोलो वो अपना शेयर करें.
Yes, sir. You can screen, share a screen.
Yeah, you need to stop the share screen and then you give me. Yeah, and also you right click on my name and give me the record permission.
नहीं. अभी हो गया देखो.
And you made me the host, right?
Yes, sir. Good afternoon to all. Shall we start now, sir?
Yeah.
Yeah. Good afternoon to all. On the behalf of IIT Agra, I, Bablu Kumar, Assistant Professor in Mechanical Engineering Department, welcome to all in 1 week short-term training program on recent trend in mechanical engineering. In the second session, our invited speaker, Dr. Prashant Kumar Jain, Associate Professor from IIT DM, and the expert giving the expert lecture on the topic Introduction to Additive Manufacturing. Now I invite Shailen sir to introduce our speaker.
Thank you, sir. Professor Jain has over 25 years of research and experience in UG and PG level. He is graduated in engineering from Dr. H. R. University Sagar in 1995 and did masters in advanced production system from Vidisha. He received PhD degree in area of rapid prototyping and additive manufacturing, particularly in part strength studies in selective laser sintering process from IIT Delhi in 2009. Dr. Prashant Kumar Jain was previously in Delhi Technical University, formerly known as Delhi College of Engineering, as a lecturer in mechanical department. He also served IIT Delhi as a project scientist and research associate, where he engaged in research work on error compensation in CNC machine and part quality improvement in fusion deposition modeling. Currently, he is with PDPM, Triple IIT-DM Jabalpur as an associate professor and dean student welfare. He has more than 100 publications to his credit. published in international peer-reviewed journals of repute, national and international conference in India and abroad. He has guided 5 PhDs and 25 masters and several ongoing. He has been a resource person and delivered invited lectures, chaired scientific sessions in several nations, national and international conferences, short-term training programs, and QIP programs. His research interest extends from geometrical modeling, CAD-CAM integration, incremental sheet forming, computational geometry, rapid prototyping and tooling, incremental sheet forming to nanotechnologies in manufacturing. I would like to request Professor Prashant Jain sir, please start this session.
Yeah, thank you, Dr. Sailendra and all organizing team members. Thank you for keeping technical education alive even in this pandemic situation. This gives us a lot of opportunity to interact with each other. And in today's session, I'm going to talk on the additive manufacturing process. So I thought, depending on in between, I would try to collect the response from the audience. So accordingly, I may increase or decrease the content as well. So,
Sir, there is an echo from your side.
okay. Let me little bit more close, so I hope no echo will be there.
Okay, okay, sir.
Is it okay? Is it okay, Dr. Salen?
Yeah, yes, sir. Yes, sir.
Okay, so let us begin with today's session. As we have given the title Introduction to Additive Manufacturing. So, however, I would cover as much as maximum possible about the additive manufacturing process. So, today's session we begin with first the product fabrication approaches, what we call, right? So, product fabrication approaches. Like this, we have the first machining, the well-known process. We have the machining, the material removal process. Then we have the joining processes like welding, soldering, etc. And the most common and popular process is the farm processes, right? Where injection molding, dye, etc. we make, right? Now, today we are talking about the layer deposition, that is rapid prototyping. Initially and nowadays well-known established manufacturing technology as additive manufacturing process, right? So what we do in additive manufacturing process, we are capable to create a model of an object directly from the geometry, right? By depositing one layer atop in this fashion. So the first layer, second layer, third layer, and all the layers will come one atop each other. Right. So this is in the rapid prototyping, rapid manufacturing, and now well established as additive manufacturing processes. Right. Look at this. The basic purpose of that is the communication initially when it has come as a rapid prototyping. So that's why we call it as an additive. And if we go by the classification, we can take it into two, additive and subtractive. So in case of a subtractive process, which begins with a billet or a piece of stock or material, we carefully remove the material to achieve the desired geometry. But the process may be complex. Part geometry may be very, very complex. The process may be very time consuming, exhaustive, and sometimes very expensive also, as we are removing the material in a form of chips, which is now converted to a waste material. No use for that, right? So in this situation, we prefer additive manufacturing as well, where we, instead of removing the material, we add the material, we deposit the material. Right? So you see on the bottom the figure, in some situation even the CNC machine cannot reach to these complex parts, right? This is the CNC milling portion, so some portion it will not reach, right? So here in this case we go for additive manufacturing process where we deposit the materials. Like, so here we have two nozzles, one for part material and one for the support material. So these overhanging features can be provided support, right? So we these two nozzles will deposit. A little detail on that process, FDM process. But before that, you look at this. What the main advantage we gain from the additive manufacturing or rapid prototyping processes? You see, the complexity is no more limitations, right? Whatever the product we can think of, whatever the geometric model we can create on our system, that we can fabricate, right? So look at this here, this temple structure, right? In this case, right? Some toy model on this side, right? So anything which we can plan, which we can understand, which we can imagine, which we can think of, can be become a reality in the form of a product. Like here you can see the hut model, right? So we can see with colored components, colored parts of the hut in different colors, right? Look at this functional springs in different color. So these are functional in terms of stiffness as well. and as I said, initially we developed this rapid prototyping processes for communication purposes. So for example, if you look at that, suppose you want to have a table fabricated by a carpenter, and you reach to the carpenter and how you try to explain him about the table size, the drawer, the etc. or a cupboard, right? You immediately take a pen and paper and you try to draw something, right, to communicate with that. So that's why what we call is that a picture 1,000 words, right? And here we are going beyond the picture, right? So beyond the picture means what we say, a model is worth 1,000 pictures, right? In this case, right? So that's the advantage we gain for a communication purpose. Okay. Then let's come to the principle of the additive manufacturing process. If we design something, so we can have this kind of CAD model, maybe in the ProE, maybe in the CATIA, Unigraphics or AutoCAD or anything. So once we have the CAD model, as we talked about the process, we want a layered information, right? Our task is to get this kind of contour layer information, right? This contour layer information, we have this information. So we want a cross-sectional contour of a product. If I have this product in my hand, a teacup, so that cross-section of this component is required, right? And in this case, what will we having in the cross-section, since it's a teacup? So suppose even you forget about this handle, then we will be having as a cross-section two concentric circles, right? In that case, again, two concentric circles, this top portion, when we get from the top view, we need to fill the material. Say, for example, this is the cup, cross-sectional, so we will have two contours like this. And in between this material has to be solidified or deposited, right? So that is the part we are going to fabricate. Here, what the point I want to make it clear is that we need to solidify this contour material, right? So cross-sectional information need to be collected, and after that cross-sectional information, we need to deposit the material accordingly, right? Fine. So based on this, you see the lot of tapered edges are there. So these need to be squared, right? As for additive manufacturing, we will not be going to fabricate any tapered layer, right? We always have this kind of extrusion, so we can deposit material that will be in vertical in position. So once we create all these layers, our next job is to stake and pasting them. So you see on the bottom, these layers are joined with each other. Staking has been done, and then some glue material or maybe other mechanism, the pasting has been done. So what happens here, once we do all the pasting, that's the resultant model, right? We started from this, but we landed with this, right? Here we have a complete smooth surface, but here we have the lot of stair steps, right? That is known as stair stepping effect. Today we will not discuss on this stair stepping effect. Here in this also you see the perfect cylindrical hole is there, but what happens because of this layered structure, right? So these situations will occur, but the difference we have to observe, what we designed, what we have intended is this, but what we have received is completely different. Lot of surface roughness or stair stepping effects could be there, right? So a lot of research going on in this, and a lot of requirements to receive this finished physical prototype. Here we need to do the machining, we need to do the polishing, grinding, or anything on this top surface, right? And this will depend on very along with the orientation kind of thing, right? Different orientation, we will have a different surface finish, etc. Right? So this is all about the principle basically, and what principle says we should have a geometric model and we should have a cross-sectional information, right? Where the material to be deposited or solidified. Look at this. If we talk into the terms of process chain, you look at this here, this is the first cylinder. Anybody can identify the difference in these two cylinders? Anybody would like to respond? After geometric model creation, we do the next step, but can anybody differentiate two cylinders from the participants? Can anybody differentiate in these two cylinders?
Sir, participants are not allowed to unmute their mics.
Oh, okay, no problem. We can allow them to interact because
Okay, sir.
Yeah. If possible from your end, please allow them. Somebody is writing in chat as well. Yeah, let me see in the chat. First is the circular,
Okay,
second
allowed है sir. ठीक है.
Yeah, I think allow it. So whenever we want, otherwise anytime we can keep them unmute or everybody, no issues.
Yeah, allowed sir.
Yeah,
allowed to unmute them.
My screen is visible back where I stopped. My screen is visible to the back same position or not?
No, sir. Your PPT is not showing.
Yeah, because I have just changed. So let me see again. I hope now my PPT is visible back.
Yes, sir. Yes, sir.
So from participant side, somebody says it's a complete cylinder, and in another situation, it's a polygon type. Anybody would like to add anything? After 5-10 minutes, I will come back every time to the participant. So we can keep session active, not only one-way communication. So any participants would like to say something on this? What is the difference in two cylinders? I hope now you can unmute yourself and you can talk to me. First circular and second is polygon types. right? So you see here, it's a complete smooth cylinder. And in the second case, it is a converted into the polygon. So we call it a tessellated model, right? This is the tessellation has been formed on this, right? So you see this complete cylinder has been cut like this and again converted into two triangles, right? So this is known as the tessellation, and tessellation is a piecewise approximation of the surface, right? So once we have this kind of piecewise approximation, this will help us to do for the tessellation, right? Right. So this kind of tessellation surfaces we already talked on previous slide. After this tessellation, you look at this cross section will go like this, your plane, right? So with this cross section, what is happening now? You are calculating intersection of this plane with these polygons, right? And here the polygon is itself is a triangle, and the triangle is again converted into two lines. Look at this. Now your intersection will say these are the 2 points which are intersecting for this triangle, right? Now we can apply for a for loop, and now we can have a number of triangles can be calculated in this way, right? And then we can arrange them in a logical sequence, so we can get the contour information, right? Once we get this kind of contour information, we can generate successive contours for each and every layer, right? And now once we get this contour information, say for example, this is the contour information, right? Then the second thing is required is that we need to generate the slicing like this. So this is the nozzle path we will able to generate, right? Got it? So in this way, we will be able to generate the nozzle path, right? So then we have a tessellation, then generation of laser scanning path, and then we have the part fabrication, and then we have the post processing. So once we complete this nozzle path, then we will convert this into the GMN code or any other method to supply to our 3D printing machine, right? Then material will be deposited in the form of a rod, right? Once this material is deposited in the form of rods, then part will be fabricated after removing. Then we will take it to the post processing and finishing, right? Based on this post processing, we will remove the support materials generated, any other burrs, etc. Then we can check and test the prototype. If it's okay, fine. If not, then we may require to change some CAD modeling of the part and then complete this cycle. So this is a closed loop cycle for overall rapid prototyping process to be done, right? Let me show you in one of the video as well. So how we proceed layer by layer and how we deposit the material and particularly in selective laser sintering process kind of thing, unsintered powder is provide the support to the overhanging features, right? So here challenge is the overhanging features. And if participant have question, please keep on typing in the chat box. So if I have sufficient questions, I will come back and I will answer them, right? So this is about the principle, right? Then we will come to the various processes of additive manufacturing processes, right? So before that, look the implementation part. See, whatever we talked, this is the geometric model we have taken, right? Designed in a Pro-E kind of thing. And if we cross section it here, right? So once we import this model into the MATLAB or any other programming for the purpose is for slicing, right? This is the part created in Pro-E. Now look at this here. If we take it into this slicing mode and then we cross section it. Since we have already tessellated, converted this into the STL file, so it have the only triangles, right? So you will get this intersection like this. And then we need to arrange them in a logical sequence, right? So look at this. The same STL model now in the form of a triangles only. So you can see the red colors are the lines of a triangle. There is a green color. And this green color is the plane for which intersection has been taken, and the blue color dots intersection point for this model, right? So once we take and we plot them in a random order, right? Random order means as and when they calculated the intersection, we plot it. Right? So once we plot it, we get this kind of information. But this information is no use for us to get a 3D printout, right? So what we do, we need to convert this information and join all these points which we have found over here in a logical sequence, right? Once we connect them in a logical sequence, look at this. This blue color contour is the external contour on this position, right? If we cross section this part at this level, right? Right? What will happen on this situation, right? With this cross section, we will get this blue color contour for the outer, the red dotted color contour for the internal, right? So this is the internal, right? Similarly for this cylindrical part, the outside contour and the inside contour like this. Yeah. So that is the contour information we have got for any typical part, and in this way we get. Now the next task would be to get the nozzle path where the material will be deposited. So look at this red shaded portion to be solidified, right? You can relate with this figure, right? To fabricate this part itself, you require this to be clear. So in this case, if my nozzle laser beam passes through like right from here, say. So what will happen here? The laser beam will be switched on. Here the laser will be switched off. So in between this, the part material will be solidified. Now here laser beam will travel, but the laser beam is off. Then again switch on here for this portion, right? And if you consider as the FDM process, then it would be a nozzle, right? So if this nozzle, then it will be open here. So material will come out of the nozzle. Here the nozzle will be closed. Then again on off kind of thing situation will be there, right? So where it is crossing this contour, right? On, off, again on, again off, right? So that is the situation happens when we talk about the tool path generation, nozzle path generation, or laser beam path generation, right? So this is all about the principles, right? Let me show you this on the software. I hope my entire screen is visible to you.
Yes, sir. Right now, screen is not visible, sir.
Right now, my desktop would be visible, not PPT screen, right?
Yes, sir.
Right. So if I open something else, that is what I want to check actually. So if I open some other software, it should be visible to you. Right? Can you see my screen now? Yeah,
yes, sir.
It's not PPT screen. Right. It's not PPT screen. Right. Look at the part I was showing you on the screen, right? This is in the Magic software, right? This is the part we are going to say, for example, in fabricating, right? So you can see here there are 3 balls inside each other, right? Okay. So these 3 balls are to be fabricated, and which is possible only with the SLS process, so that without any joint, and these moving 3 balls would be created, right? Now look at this. If I show you the cross section like this, uh, Look at this. This is the contour we are going to receive at this particular height. So look at from the bottom, what we have explained so far. The first would be a circle, another circle like this. Every contour this with blue color, it is going to be fabricated or solidified. At this height, what is going to happen? We will have only this much portion to solidify. So here only in this area, the laser light will come and it will deposit, right? Now you see, and this to this information, what is happening? Only the first layer is, only the first sphere is getting fabricated. Right? Now if you move further, you look at this, the second sphere, the third sphere is come into picture. The blue color contour you can clearly see, right? So this is the information we need to collect, we need to generate from a geometric model for additive manufacturing process, right? And slowly it will keep on up to the top layer, so that you see the first sphere is complete, the second, third is complete. And lot of good information, good knowledge in case of STL file. So look at this, you can see here the bottom portion you have written the IIT Delhi, right? So a lot of manipulation should need to be done, right? To write some text or modify your STL file. And if you look at here, you can have, you see the triangles, right? This is all STL file, what I have shown to you earlier. Look at this. You all have here is the small triangles, right? So this surface is converted into the small triangles, right? So when we have the section information, we will have all this information. Sorry. Look at this. Oh, sorry, I have changed this. Look at this. This type of cut would be there. You can see the two triangles there, and this blue color plane will go and it will collect the two intersection, 2 point again. And when we join them in a logical sequence, we will have this entire contour information, right? So that is the purpose of STL file, tessellation, and getting the contour information. And that is very much required for 3D printing or additive manufacturing, because we want to produce it in a layered form, right? Okay. So if at this moment, if we have any question, please ask. Now we will switch over to the FDM process and SLS process. Right, that I have already shown you in the software screen directly. Yeah, this is the original model. You can see the EOS electro-optical system model. Now we move to some common additive manufacturing processes, right? So we have a broad classification of these processes, like we have liquid-based processes. Then we have, for liquids, we have the stereolithography process. Then we have solid ground curing. Then we have the solid-based fuse deposition modeling process. And then we have the laminated object manufacturing process. Then we have the powder-based selective sintering process and selective laser melting processes, right? So see on the first, the fuse deposition modeling process. What we have in the fuse deposition modeling process, it's a solid-based process, and overhanging features. Look at on this part. There is a hanging feature, right? So this is the part to be created, right? Part model. So for this overhanging feature, we require the support to be generated. And here we have the two model spools, 1 and 2. One for support structure and one for part spool structure. These are the heated rollers. They will push the wired spool towards the heated extrusion, right? So here the heated extruder is there. So from this heated extruder, there is a nozzle on the bottom side. From nozzle, the part will come out of this material, right? Let's see this in a form of a video. Right, this is the FDM process. In actual practice, it is not that much fast when we run the FDM machine. This is for video purpose had been made the fast. Nozzle move very slowly. Right, look at this, the some of the components we made. And here we require a lot of expertise for making such kind of close tolerance parts. You see here, these parts, right, the open. Everybody knows this part we already have in our college bags, right? And here this flexural strength is required so it can compress and lock and you can open it, right? So a lot of closed tolerances to be matched. And because in FDM process, when we fabricate these parts, depending on the vector length, material, particle strength, particle size, thermal conductivity, etc., a lot of shrinkage will come. Our expansion will come. So depending on the work envelope, the part may be shrink, our part may expand. So to achieve the proper fit, we have to find out suitable process parameters, right? These are some other images we developed from the biomedical applications using CT scan and MRI images. So you see after the accident, there is no bone in this area. So these things we have extracted from the CT scan MRI. Here you can see the lot of moving components, right? With close tolerances have been made, right? Some biomedical components. Here is a fully functional assembly. You can see you can rotate this screw and adjust your spanner, right? This spanner. So this depend on this, how close tolerances you have been able to achieve. Now we come to the SLS process. This is very important process because this is the process which shown the potential to become a complete rapid manufacturing process, right? So this is the power in this SLS process. You look it on this center figure first. We have the galvano scanner, right? And we have the laser beam, right? So from this laser beam, laser light has been guided on the build platform. That is the build platform. Completely, this is the build chamber, and within this, the build platform. So every time when one layer is fabricated, this build platform goes down by the one layer. Here is the closed chamber. So in this closed chamber, infrared heaters installed. Those infrared heaters keep the complete build chamber and the unsintered powder heated just 4-5 degrees centigrade below its melting temperature. So in the selective laser sintering process, powder is not completely melt. It used to sinter. So two powder particles join with each other just by sintering. So the neck formation will take place and the powder particles will join with each other, right? So in this case, 4-5 degrees centigrade remaining temperature rise will occur by this laser line. So this process starts with the powder spreading by the recoater. You see here, these are the solidified layers you can see on the bottom, right? And this yellow color is unsintered powder, and that is the build platform. So every time this build platform will go downward by one layer, right? So in this situation, you can see here, this powder recoater have the powder, and if we talk about the polymer material, we have the powders available in 40 to 60 micron. So with 40 to 60 micron, this layer has been sprayed on this. You can see this top layer, 40 to 60 micron, and then we have here again this powder is deposited. Right now, layer is formed. Now the laser light is coming only to the selected area. So what we discussed so far is that the powder is already heated just 4-5 degrees centigrade below the melting temperature. Now this 4-5 degrees centigrade temperature rise come from this, right? And what has happened here after this, this material will become solid. Right? So once this material becomes solid, this platform will go again down by one layer, right? Right. So once this is down, right, you can see the completely solidified layer, right? Now what will happen? The recoater will again come, and this recoater will fill the next layer, right? So this recoater will come, the next layer will come, then an infrared reader will be switched on, and once this infrared heater is switched on, this will again maintain the temperature at per the requirement, right? Look at this with some video. And since this is FDM, instead of FDM process, in SLS process, you see, look at this, this kind of overhang features can directly be made. We don't require this kind of support. This support is not required. Anybody could tell why this support is not required in this case of the selective laser sintering process? Anybody from the participants? Yeah. Already unsintered. Yes. Correct answer. There is already unsintered powder is there, right? Let me go back to sharing of my screen. Right? So I think my PPT screen is visible to you all.
Yes, sir.
Look at that. You can see the entire process. This we got accidentally. So that because of the clay experiment, this laser beam has become reflective. You can clearly the solidification takes place. You see, this is the recoater spreading new layer of the powder. And this is infrared heater was switched on. So it will again maintain the temperature when new unsintered powder layer is formed. It has to again keep at the temperature. All right. So this is the process for SLS, right? Here are so many process parameters are there, right? So these process parameters has to be carefully controlled to have the powder material to be properly sintered, sprayed. Right over here. So here the laser power, beam speed, hatch spacing, many things, spot diameter, just like our CNC machining, beam offset, hatch better to be controlled properly, then build temperature, preheating time as well, right? Once we able to control all these process parameters, we can have a successful part print. Now look at this, these are the some of the parts made on the SLS process, right? Here what has happens every time when we print the new layer, the previous layer has to be remelted in a partial way, right? So this is the deposited layer and this is the powder substrate, right? So when this laser light comes, this is the melt pool or say centering only. So this much portion of the pre-sintered layer has been remelt or resintered with the new layer. So the bond in the layers can be achieved, right, in this position, right? So here these are the two particles, right, and this is neck formation has been observed in the two particles so that they join each other, right? Now see the effect of layer thickness. If you keep on changing the layer thickness or the energy density, quite possible, right? Here if you see, this is the variation in the energy density, right? The energy density is 1.85 joule, and here the 3.3533 and 6.43. So the energy density is keep on increasing. Energy density means the energy we are supplying at particular location. So when it is less, you can clearly observe just like a braid packet, gap is there. Second is perfectly solidified, but still you can observe some gap between two layers. So possibility is like that, it delamination may occur. But when you increase further, this is a complete solid. No delamination, no gap, or no separate layers we are able to identify. Point is here, you can't increase this energy density for so long, right? At certain limit, because beyond a certain limit of this energy density will start deteriorating or burning of your part. Our unsintered powder will stick to the sintered powder. So this will lead to the dimensional accuracy. Your part will become oversized, right? So these are the issues with energy density, right? Now, if you have any questions to this level, we can interact right now. Otherwise, we will move to the application part of the additive manufacturing. We discussed the principle, we discussed the data preparation, the STL file requirement, and the slicing to be taken care, right? And then we are coming to the application part. Look at this, if I go even for the slicing as well, we can generate all this information, this data on our own system. Need not to go for any third party software, right? You can have a STL file, you can open it and you can cross section it. right? So let me also show you some. Yeah. Right, look it for this. If I run this program, I can have an STL file on my system, right? Just like any other commercial software kind of thing, I can open an STL file. And the first, let me show you a simple full pyramid STL, so which will be very easy to understand for you, right? It knows that what is the height. So let me select the height, say for example 34. Look at this. This would be the geometric model of your STL file, right? This is the cross section you got, right? So you have got the head and tail approach T1, T2, T3, T4 at H1, H2, H3, right? And then the next task is to connect them in a logical sequence. This is a very simple file, so you can look at this. Right, and after that it will join in a logical sequence. You see in the third figure, you can see the black color contour is there, P1, P2, P3, P4. So this is the cross-sectional area or layered information you got at this particular height. Now, if I run this program in successive way, we can get the entire information, right? And now if I take any other typical component, you look at this, we run this program again, right? So we can have any typical component like this. Let me show you the half cut. So you can show the typical part. Let me put the height as 24. Look at this. This the typical part you are going to have. See how many intersections are there, and you can connect all them in a logic sequence. Right, and the next task is to get a contour information connected in a logical sequence. So you got all the intersection points here. Right, so right, you can see on this black color contour is there, and so many, more than 62 points we can see here, right? Information will go to our 3D printer, right? So let us close this. Yeah. So if no more question at this stage, we can go back to the contour information. And then we let us go to this. Yeah. Look at this, some typical applications. Look at on this part, how good if we have all of us might be working on the ANSYS or COMSOL for this kind of stress analysis. How good we have this analysis done on our system in a 3D part, right? And we can have a 3-dimensional model. And we can have 3-dimensional model at here, right? And with this 3-dimensional model, we can rotate, we can have in our hand, and we can analyze the stress analysis. Right? So that we can perform the form and fit analysis, the flow analysis, the stress distribution, the markup, diagnosis, surgical planning, operations, and then fabrication of custom processes and implants, etc. Right? Look at this here, the truss geometry is there. These kind of truss geometries can be fabricated. We can generate the scaled model, apply load, and do testing. Here you can see the fully functional hearing aids are there. Right? These hearing aids cannot be made as a mass production, right? Because these will be different for every person, every human being. A different dimensions would be there, right? So in this case, you require CT scan data or CBCT scan data, and then based on this, we can fabricate, right? Then you see some more typical components. Again, different shape hearing aids are there. This is the cable fixture. You can see here the lot of joints are there, but they are not assembled. Nothing has been joined, right? The part has been made in this way, like on the SLS process, so that the tolerance in between or the margin has been left for the joints, right? So in those areas, unsintered powder would be there, right? And after completing the part, we remove it and we clean it using short blasting machine, air guns, etc. So that powder particles are removed. And now our component is completely functional, right? Without any joint. See here the typical components of washing machine rotor. Here you see the housing for the drilling machine, and very first figure also I have shown the same drawing, right? Look at this, how many drawings required for this cross-sectional view to be supplied to your manufacturing section to develop its die, right, for injection molding. You can see here, this is the car seat. Of course, normal machine does not have this much build wall. People are still trying to develop the software or some decision support system where we can put the cut like this. So this car seat can be built in 6 parts, and automatic ratchet kind of things can be attached. So we can just join them, just like our most of the pens or some your say remote assembly or your phone assembly. You see, you just keep 2 parts on the assembly and you can just press them. They are joined, right? So these are the typical applications. Look at this here. We will have some big assemblies, some gear assemblies we can fabricate, right? Now, similarly, you can see some structural models. We can have this kind of a structural model on the top of this building. You have this truss model, so you can also separately you can do. Here you can perform the wind tunnel analysis or flow analysis or anything else, right? Now see some more architectural model, the house designs, the building designs can quickly print it, right? Can be shown to the your customers, right? How your house will look like. You can see here that the door openings can be how clearly mentioned and explained to everybody in 3 dimensions. Right? People can have these models at their home before building their house. You can see here in this the stairs view, the windows view, right? Then look at the actual very huge size printers are there. Here you see this is the 3D printer which is depositing the concrete directly, right? And this is a huge gantry type 3D printer where it is depositing the concrete directly, and the house can be built, right? So this is a huge size printer. Now come to some applications in 3D metal printing kind of thing. Look at this, there are 2 components. Now every participants have to unmute yourself and let me know how many parts a casting be made and assembled to pour this material. right? You can have a pattern, and then if you apply the casting, so that casting should be opened to remove this part, right? Say if I have this cup again, right? Handle is there here. I can have the casting of this part in two components, right? So I can have this much, two components, right? So I can have a parting line from here and this cup, right? So based on this parting line, I can divide this cup and cut section in two parts, like this. So one part will be open in this way, another part is open in this way. And this part will come out of the casting. Look at this here, how typical components are there. You see here, the undercut is there. You see this slope is again going in this direction. Right? So how many parts we can have? You can unmute yourself and answer these questions, and if you have any more questions, you can also ask at this level. Look at this one here again. You have a very typical components are here, right? So you require a typical casting. Is small components. They are joined by screws or some small welding. Material be poured, and after solidification, you have to broke that casting. Then only these parts will come. Here, what the advantage has been given by the additive manufacturing processes: no pattern, no cast, nothing required. You can deposit the material layer by layer. But still, it is a very, very costly affair, because when we talk about the steel materials, this is a high-speed steel used in 20 micron size, right? So based on 20 micron size, what is going to happen? A lot of material, lot of powder material will be wasted. In case of polymer materials, we are able to reuse the unsintered powder. But in case of metals, a lot of microstructural changes occurred. The neck formation characteristics has been lost after one heating cycle. So that powder of the steel material cannot be reused. And further, these kind of components join with the build platform. So you need to cut with the wire cut EDM machine, right? So a lot of other accessories are required. And in case for metal, to avoid any oxidation, that build chamber should also be in completely closed in inert gas environment. So a lot of nitrogen to be supplied. You need a complete nitrogen generator, and for nitrogen generator you require a chiller unit so that you can maintain the temperature of the nitrogen generator, right? So it's a very costly affair in case of 3D metal printing. But these components are for some aerospace engineering or some cryogenic engine or something else. You can't wait for a month to develop the casting, then pour the material, then you get the forging, and then you do lot. We need to go for additive manufacturing process in such situations, right? Then see very small components of a micro size and with micro features. On the behind the finger, you can see how small features are there. This we already shown you, spherical ball, inside ball, and this from this hole the unsintered powder has been removed. Then look at this, the micro fabrication. You see the small size. You see the flexible components, like they are the chained component. You see a lot of movies nowadays, right? Like Tanaji or Padmavat, where a lot of kavach kind of things are the warheads are to be worn by the artists, right? So they are not coming from any museum kind of thing, right? They have to be built, they have to be manufactured using such additive manufacturing technology, right? Look at this here, a small screw of titanium. This is used to implant in a human body. But the requirement is this: for tissue to grow and to pass through these screws. Look at this here, the through holes are required. Even for the cross section, you look at right? These are the through holes. These holes, small size holes, cannot be even built by the wire EDM. Right, so these are the typical applications of additive manufacturing in a metal additive environment. And recently people have found this in case of polymer as well. We can have such kind of body parts to be built and prepared with this, right? So from here you see, you can clearly also observe the layers in this, right? And then you look at this, some of the skin color parts has been fabricated to be implant as a artificial prosthetic implants for the human beings. Look at this. This is the latest development in a glass printing by MIT USA. You see here at 1200 degrees centigrade how nicely the glass is coming out of the nozzle. Right, and these are some glass patterns has been created using this additive manufacturing process, right? So we have covered three parts: the basic principle, data preparation, STL file, etc., how to do the slicing, etc., and software use. Then we covered two additive manufacturing processes which are most common nowadays: the FDM process and the selective laser sintering process. And then we have covered the various applications of additive manufacturing processes, right? So I think this much would be sufficient for today's session. And with this, I would like to thank to all the participants and the organizing team. And if we have any questions at this moment, we are open to take few questions.
Participants are requested to, you can unmute your mic and you can ask.
Now I have. Yeah. So if no more questions, we can close the session. And if any participants have any questions, yeah, please, you can unmute yourself and you can switch on your video as well.
Hello. Sir, I am audible?
Yes, Mr. Kumar.
Sir, I, Bablu Kumar, Assistant Professor, Mechanical Department. Sir, I want to know it is possible to manufacture the FGM material by using the additive manufacturing process.
FGM means what?
Functional graded material.
Yes. People are working with functionally graded material, particularly in case of SLS process, where you can vary the material properties depending on some functions in particular location. Right. So you can control the laser velocity, laser power, and the hatch spacing, etc. So you can control basically the energy supplied at a particular location. Based on that, you will have a different density and different mechanical properties. So in that way we can fabricate. And in FDM process, very limited functionally graded, you can say, just like by varying the layer thickness is possible. So that would be the case for.
There is one query from Mr. Arun Gaur. He just want to ask, can we use any type of material in additive manufacturing?
Yes, we can use any type of material provided it is available. If we talk two processes, for FDM process, you require a wired spool. Recently in our lab, we have developed a new system on CNC machine in which we can have a wired spool kind of thing. So we can deposit the material on the nozzle itself, right? Let me show you a video. Let me share my screen again, and I think I have closed the PPT. Okay, no problem. Let me run a video only instead of going to PPT. Look at this deposition video. This is newly we have developed on our CNC machine. So here you can see there is a heated nozzle is there, and from outside we are giving the heat, and inside this on the top there is an extruder head. So instead of wide spool, we fill the pellets of the ABS, right? Now this ABS pellets are meant within this fruit, and on the top there is a screw which is directly connected with the CNC milling machine. So that material is coming out of this nozzle, right? Look at this. You can see the material is deposited in layer, right? So point is here, if you talk about any commercial machine for FDM, you required a wired spool. If you talk about the SLS process, you required a powder available in a particle size, and the material should have a tendency for neck formation and join with each other. So any materials means that should be available in that with those properties, right? So this is the case in this. You see, this is a CNC machine converted into the additive manufacturing process, you can say here. And that we have done for hybrid machining. So on the same setup, we are capable to do this kind of machining as well. Look it on this on the same build platform. This is the material deposition takes place in the previous video. Now on the same platform, the material removal is going on. Right? So this is the point I just wanted to mention over here, that there is no problem. We can use any material provided we should develop such facility. Right? Let me stop sharing. Yeah. Yeah, of course, there would be a difference in the properties because there would be a lot of porosity in this case. Yeah, please continue. Somebody was saying something.
Okay, so there is a one more.
Yeah, please.
Regarding the properties, that
yeah, definitely the properties will change, will occur, because when you go for injection molding, what happens, your polymer material is compressed completely, no scope for porosity, and here you are depositing the material without any force applying. So in built there is a air gaps, bubbles, porosity, so the density of the part comparison to say for injection molding will be less. So of course the strength, if you compare with that conventional machining for a particular part, in this case of additive manufacturing, it would be less, right? But it gives you a lot of opportunity to redesign the part in such a way so that even if you produce the part using additive manufacturing, still if you give you the sufficient strength to sustain with the application, not comparison of the other processes. Like if you built a chair, plastic chair from additive manufacturing process, lot of issues may be there. Some delamination may be there, some deflection may be there, distortion may be there. So you can have, right? So this is not for basic purpose that you should build your own teacup by this, right? But in my case, I used to print a lot of mobile stand for my purpose. Today I thought, okay, in this mobile stand I am not happy. I just want a mobile stand which have a gap also so that I can charge my mobile, right? Suppose I am taking Zoom meeting on my mobile, so I want, okay, this angle should be 5 degrees more tilted like this. So these kind of design iterations I do, and I need not to wait for somebody else to fabricate my mobile stand using injection molding. For that injection molding, he need to develop the dies first, then CNC machining for dies. Many things are required. Here I can have a direct printout of those components, right? So that's the situation. Yeah, okay.
Okay,
Dr.
thank you,
Salim,
sir. One more question from Priyesh Mishra. While making any prototype, is the step of tessellation before slicing required every time? While making any prototype, is the step of tessellation before slicing required every time?
If you can have a direct slicing, no need for tessellation. Tessellation is an intermediate step to facilitate the slicing actually, right? If you can do the slicing, it's no problem. Suppose, for example, you want to build this kind of part. This is a perfect cube, right? And you want a cross section of it. So this is a simple information available. Even you need not to make a geometric model of it. What what the 3D printing machine is required, the contour information. So if you can extract the contour information of this product, you know already on the top it is a square and it will be entirely, it would be a cross from bottom to top. No need to go for tessellation. But suppose you have this kind of component. You recognize what is that component? Anybody from participants? Can you see what is that component in my hand? No one?
Computer mouse.
Yes. Look at this, how it is typical. अब अगर मैं इसका क्रॉस सेक्शन यहाँ से लूंगा ना, तो इस क्रॉस सेक्शन लेने के लिए इसको कई सरफेस, that quite possible it might have a Bezier surface or B-spline surface or hyperbola, parabola in this section. In this section, it may be hyperbola or ellipse, right? So in that case, this problem will be very, very complex for me to get its cross section, right? To avoid this situation, what we did, we do the tessellation. Tessellation ने क्या किया? Piecewise approximation कर दिया और आपके सारे surface को triangle में convert कर दिया. Now, what is there in the triangle? Only 3 lines. So, calculating of a cross section from a triangle, it becomes more easy, right? So, it's not just simply like you are cutting a fruit kind of thing from here, right? You have to cut a geometry and a lot of computations are required, right? So, if you cut it like this from here, right? So, you need to solve various equations which are defining this mouse surface, right? Yeah. Yeah, okay, Dr. Salim.
Yes, sir.
Yeah,
I think
we can close.
participant has solved their queries, and Professor Jain sir has very elaborately described the various processes of the 3D printing. Participant, if you have any query, you can just put in the chat box, or you can just, I will share the contact details of the Prashant Jain sir.
Yeah, I have already in the thank you slide, I have already put my Facebook ID is PKGen 2006. LinkedIn is again same PKGen 2006. And the Gmail is also PKGen 2006.
Okay. There is a one query from Mr. Vijay Raj Pilania. Tessellation is just
Yes,
similar
correct.
to meshing in FEM.
Yes, he is correct. Only thing, you can have meshing in a different way, different kind of meshing you can do. But when we do for tessellation, we use triangles because this is the minimum size plane available. If I have a square, if I have a rectangle, there is a quite possibility of volumetric loss. Actually, we need to go in much depth. Why we are taking triangle only for tessellation, right? Why not a square? Why not a rectangle? Why not any higher order polygon of pentagon or hexagon? Now come back to the reverse. Even this square is cube is there. Still we can have this face, right? No volume loss will come, but still we will take it in a triangular way, right? So that require one full session. I used to talk about the tessellation only. How to do the tessellation, the Voronoi diagram, the Delaunay triangulation, what is the rule to follow the tessellation. But he is right. It is very much similar to the meshing done in a FEM analysis.
Thank you, sir, for your wonderful session and giving us so much knowledge on the additive manufacturing. And we are hoping for another session in upcoming months for completely based on the additive manufacturing. So I would like to thank Jan sir for this very good session.
Yeah, please.
Yes, sir.
I think so that we can end this meeting.
Yes, sir. We can conclude this meeting, sir. Thank you, sir.
Yeah. Okay. Thank you. Thank you. Thank you, everybody.